Hi everyone. Here's a sample circuit problem that shows how the equivalent resistance concept can be useful in circuit analysis. So look at the following problem. We have a 30-volt power supply, and so we've got current leaving the 30-volt power supply. At this junction I've labeled B. Some of the current will go this way, some of the current will go this way. So we've got these two parallel paths. The current comes together, and then all comes through a 9 ohm resistor and flows back into the power supply. So basically we have a parallel connection that's in series with another resistor. So our job is to basically find out everything that we can about this problem. So among other things, we'll find the current everywhere, both through these resistors and the total current leaving the power supply and entering the power supply. I also want to know the power delivered to the circuit by the power supply and dissipated by each of the resistors, and as a check we'll calculate the total power dissipated by the equivalent resistance between points B and D in this circuit network. The first thing to note in this problem is that without using the equivalent resistance concept, we'd have a hard time getting anywhere. If we knew the current leaving the power supply, we know that some of it's going to go this way and the remainder will go this way. And we can know what proportions would go each way by using the fact that the voltage drop across the 10 ohm resistor must be the same as the voltage drop across the 15 ohm resistor because these paths are in parallel. But without using the equivalent resistance concept, we don't actually know the current leaving the power supply. So what we need to do is find the equivalent resistance of this entire network from here to here. Replace all of this with a single equivalent resistance, and then we could figure out the current entering and leaving that equivalent resistance, and then get some traction on this problem. So let's get started. First, we need to find the equivalent resistance of this portion of the circuit, this parallel connection from B to C. So we can do that using the parallel resistance formula. And we get that the equivalent resistance between points B and C, which I'll call R sub BC, is equal to 6 ohms. Now, this isn't the resistance of some actual resistor. This is the equivalent resistance of the network from point B to C. What this represents is the single resistor that I could replace the whole network between B and C with to have the same effect on the rest of the circuit. So in other words, the rest of the circuit wouldn't notice if I took this parallel connection of a 10 ohm resistor and a 15 ohm resistor and replaced it with a single 6 ohm resistor. And so what we can do is, in the next phase of our problem, we can redraw our circuit diagram and replace these two resistors in parallel with a single 6 ohm resistor between point B and point C. So here's the representation of that circuit diagram, replacing the actual resistors between points B and C with this equivalent 6 ohm resistance. Now we note that this 6 ohm resistor is in series with the 9 ohm resistor, so we can use the series resistance formula to find the equivalent resistance between points B and D, and that will be 15 ohms. That means we can replace these two actual resistors between points B and D with a single 15 ohm resistor. Now we can use Ohm's law to find the current flowing into and out of this equivalent 15 ohm resistance. That works out to 2 amps. Now you can think of, if you want, that 2 amps as being the current that flows through this equivalent resistance. You just have to remember that this equivalent resistance at some point is actually two resistors here in parallel. So by flowing through the 15 ohm equivalent resistance, really we mean flowing into point B and then somehow getting over to point D, however it splits internally or not. So really what we're talking about is 2 amps flowing in, 2 amps somehow getting from point B to point D, and then 2 amps flowing out. Now, by the junction rule, this 2 amps that's flowing into point B and flowing out of point D, that's also flowing through the power supply. So the power supply current, if you will, is also 2 amps. Okay, so let's update our original circuit diagram accordingly. So we have 2 amps flowing into point B, so 2 amps flowing out of the power supply into point B. That 2 amps is going to split in a way that we'll determine soon enough, but then it's all got to come back together and go back into the power supply. So that means we also know the current passing through the 9 ohm resistor, because we know that 2 amps is flowing into the power supply. There's nowhere for it to split up, so 2 amps must flow through the 9 ohm resistor and back into the power supply. Now we're in a position to find the change in potential from point B to point C and from point C to point D if we wanted those. We know that from point D to point B, taking this path through the power supply, we gain 30 volts. So going back, or continuing around, we have to drop 30 volts. That's the loop rule. We know that the voltage drop across the 9 ohm resistor is 2 amps times 9 ohms, which will be 18 volts. And hence this remaining voltage drop between points B and point C, regardless of path, will be 12 volts, so that the loop rule will be satisfied. So let's check that. Starting at point D, we gain 30 volts going across the battery. Then here, from point B to point C, we drop 12 volts. Then from point C to point D, we drop 18 more volts, ending up back where we started. Knowing that the drop in potential from point B to point C is 12 volts, that means we have a 12 volt voltage drop across the 10 ohm resistor and a 12 volt voltage drop across the 15 ohm resistor, so we can calculate the currents through those resistors using Ohm's law. Just a reminder that anytime you use this formula or any of its permutations, each thing in the formula has got to be referring to the same circuit element. So, for calculating the current passing through the 10 ohm resistor, I need the voltage drop across the 10 ohm resistor and the resistance of the 10 ohm resistor. For the current passing through the 15 ohm resistor, I need the voltage drop across the 15 ohm resistor, again 12 volts, and the resistance of the 15 ohm resistor. Now we better make sure that our results are consistent with the junction rule. If I've got 2 amps flowing into point B, I've got to have a total of 2 amps flowing out of point B. I've got 1.2 amps flowing this way, and 0.8 amps flowing that way. 1.2 amps plus 0.8 amps is 2 amps, so the junction rule is satisfied. The current flowing into junction B is equal to the current flowing out of junction B. And the same, of course, would hold for junction C. I've got 1.2 amps flowing in, another 0.8 amps flowing in for a total of 2 amps flowing in, and 2 amps flowing out. Before moving on to calculate the power delivered by this power supply and dissipated by each resistor, I want to talk about another way we could have found the voltage drop between points B and C. Earlier we calculated the equivalent resistance between points B and C for this network of 2 resistors in parallel, and we found that it was equal to 6 ohms. So consider this. We have 2 amps flowing into the equivalent 6 ohm resistor. We have 2 amps flowing out of the equivalent 6 ohm resistor. So for the purpose of calculation, we have 2 amps flowing through the 6 ohm resistor. Using Ohm's law, we get 2 amps times 6 ohms equals 12 volts. So we get a 12 volt voltage drop between points B and C, which agrees with what we calculated earlier. Okay, let's move on to calculating power. The power delivered by this 30 volt power supply is going to be the product of the current passing through it and the terminal voltage. So we've got 2 amps, 30 volts. The product of that is 60 watts. So we have 60 watts being delivered by this power supply. Now we also remember that between points B and D, we can replace this entire network of resistors with an equivalent 15 ohm resistor. That 15 ohm resistor has a 2 amp current passing through it, and it has a 30 volt voltage drop across it. So this calculation that we just did multiplying 2 amps by 30 volts to get 60 watts will also be the power dissipated by this equivalent 15 ohm resistor. Now there isn't an actual 15 ohm resistor, really there's a network of all these resistors, but if we did replace all these resistors between points B and D with a single 15 ohm resistor, that resistor would dissipate 60 watts. Now that makes a lot of sense, and it should also lead us to think that if we were to calculate the individual powers dissipated by each of these individual resistors, that we would also get a total of 60 watts. So let's check that. First, let's calculate the power dissipated by this 9 ohm resistor. We can use the same formula, I delta V. So we have to use, for the power dissipated by the 9 ohm resistor, we need the current passing through the 9 ohm resistor, which is 2 amps, the voltage drop across the 9 ohm resistor, which we earlier calculated to be 18 volts. So we have 2 amps times 18 volts gives us 36 watts dissipated by the 9 ohm resistor. We can calculate the power dissipated by the other two resistors in the same way. The power dissipated by the 10 ohm resistor is the product of the current passing through the 10 ohm resistor, which is 1.2 amps, and the voltage drop across the 10 ohm resistor, which we found earlier to be 12 volts. That product is 14.4 watts, so that's what's dissipated by the 10 ohm resistor. The power dissipated by the 15 ohm resistor is the product of the current passing through it, 0.8 amps, and the voltage drop across that resistor, which, like for the 10 ohm resistor, was 12 volts. That product gives you 9.6 watts, so that's what's dissipated by the 15 ohm resistor. And we note that the total power dissipated, the 36 watts plus 14.4 watts plus 9.6 watts, that totals to 60 watts dissipated, which equals the power delivered by the battery that we calculated earlier. So it all checks out. Finally, I want to note that there are other formulas you can use for the power that's dissipated by a resistor. Either of these will work, and you should check your results for each case using these formulas just to make sure they give the same result. Okay, that's it.